Hello, everyone, again, and welcome to the last presentation for today and the second keynote of the day. The keynote will be given by Francesca Dominici. PhD is a co-director of Harvard Data Science Initiative at Harvard University and the Clarence James Gamble Professor of Biostatistics, Population, and Data Science at the Harvard T. School of Public Health and co-editor-in-chief of the Harvard Data Science Review. She is an elected member of the National Academy of Medicine and of the International Society of Mathematical Statistics. She leads an interdisciplinary group of scientists to address most important questions in environmental health science, climate change, and health policy. Francisca will be giving her keynote on how much evidence do you need? Data science to inform environmental and climate change policy during the COVID-19 pandemic. In this talk, Francisca will provide an overview of data science methods to inform environmental policies. This is based on her work analyzing a data platform of unprecedented size and representativeness. She will present an overview of studies on air pollution exposure, environmental racism, wildfires, and how they can also exacerbate the vulnerability to COVID-19. Welcome, Francisca. Sorry for the inconvenience. We're trying to figure out why there is no sound. That's the nice way to end the day.
My apologies. We're having technical difficulties, and of course, I have no idea why it's happening. So let's see if I can. Hopefully, I can be able to finish my talk, and you will be able to hear me. So the second point is that methods for causal inference allow us to estimate the health impact from climate change-related exposure and identify the most vulnerable. And then we have, there is an emerging evidence of a link between air pollution exposure, wildfires, and COVID-19 that provide an additional sense of urgency. So first of all, let me make very clear that climate change and air pollution share the same emission sources. So one thing to keep in mind is that if we're trying to target and regulate air pollution, automatically we are also going to target the greenhouse gases emission they're leading to climate change related exposure like wildfires. So these two plots shows that greenhouse gases and fine particulate matter share exactly the same sources in terms of road traffic and building and industry. So what it means is that if we can do massive data science approaches to estimate the health impact of air pollution, and we can change regulation and act strict regulation for control of air pollution, we also are addressing the climate change crisis. Now, also, we have now ample evidence that when we look at data and we use the data science to inform policy, we actually have wonderful and positive results. Here you see on the left a map that shows the plot that shows how the level of contaminants in the air have been declining over time in the last 15 years. 25 years actually, and the picture on the right shows that we are breathing cleaner air, and that is all thanks to data science. So let me tell you a little bit about what we do in our team with data science to inform regulatory policy. We have one very specific question, whether or not exposure to fine particulate matter. So fine particulate matter are very, very, very tiny little particles that penetrate very deep into your lungs. And whether exposure to fine particulate matter below the national ambient air quality standard that they're currently set at 12 microgram per cubic meter are associated with an increase in mortality risk. So the national ambient air quality standard, the NAAQS, are set by the Environmental Protection Agency in the United States, but also set by the World Health Organization, and they're considered the safety standard. So if we find evidence that there is a harmful health effect of PM 2.5, a level below the safety standard, this leads to leading stringent regulation to lower the level of fine particulate matter that is in the atmosphere. The other really important question is whether or not there are subgroup of the population that are more susceptible and vulnerable than others. So to address this question, having impact on environmental policy, my team allowed and developed the largest database to date health outcome and environmental exposure. In the United States, unfortunately, there is not a national health insurance. However, for people older than 65, there is, and this is called the Medicare system. So in the United States, when you're turning 65 years old, automatically you enter into this cohort. So we know your age, gender, place of residence, and then we know every single hospitalization, the cause of the hospitalization, and the date of death. So we have been following over 97% of the population of elderly in the United States for the last 20 years. That's around 67 million for every single cause-specific hospitalization until the date of death. As I said, we have individual level information of age, gender, race, and also whether or not they're eligible for Medicaid. The Medicaid is another type of health insurance that is only available for people that have a low socioeconomic status and low income. So it's a good proxy of low socioeconomic status and income. And so then we have the postal code of residence, and that's very important because we link their exposure to air pollution. So this research data platform takes all exposure in the United States for different environmental contaminant, health outcome, and then also confounders, which will be all additional variables that we need to account for it when we are attributing additional health burden associated with exposure to air pollution. So this is a massive, massive work of, I would call it data engineering, but also a lot of intellectual and innovative thinking about data science, because we need to link spatially and temporally heterogeneous database on environmental exposure and health outcome and poverty, socioeconomic status, and other risk factors. One important contribution in data science and machine learning that we made and we are continuing to make ourselves and many of our colleagues around the world is how do you use machine learning to estimate exposure to air pollution? So this map shows the geographic location of the monitoring station in the United States that measure daily levels of refined particulate matter. So you can see that we have several thousands of monitoring stations. However, there are parts of the United States that air pollution is not measured very well. But on the other hand, as I mentioned to you, we have our data for 97% of the US population. So we wanted to make sure that we can measure their level of the level of pollution that they breathe, even if there are people that are living far away from a monitoring station. So there is a very extensive field of research, not only on my team and my colleague here is Joel Schwartz from the Harvard T.H. School of Public Health, but there are many, many investigators all around the world. They are now leveraging information from satellite images. So we take satellite images that have a 1 kilometer to 1 kilometer daily measurement of what we call aerosol optical depth. It's an imprecise, it's a proxy measure of air pollution. We take weather data, land use data, we have output of atmospheric chemistry model, and we train a neural network on the monitoring data and be able to estimate with high level of precision at 1 kilometer grid exposure to fine particulate matter. Now, another area of research that it's called ensemble learning, and is also the idea of basically combining and averaging many existing and very well validated data science and atmospheric chemistry model that estimate exposure to air pollution. This is just an example of the many models that exist by other teams and the importance of ensembling and averaging them to have a better exposure to fine particulate matter. So we get now a 1 kilometer to 1 kilometer meter a daily level of fine particulate matter for the last 20 years. So we link to the Medicare data, and then we conduct very recently, this was a paper we published a couple of years ago, an analysis that estimate the causal effect of long-term exposure of fine particulate matter on mortality risk for over 60 million Americans followed for over 20 years. So this paper is published in Science Advance, and you can, of course, access it, as well as we have all of the code publicly available as well. So basically, we had more than 68 million Medicare enrollees. We followed them from the year 2000 to 2016 with data that with place of residence in over 31,000 zip code. And as I said, we call it about an open cohort because every year as a new American turns 65, they enter in our cohort and we can follow their health experience. So as I said, we have 68 million Medicare enrollee. We have over 38 million that are exposed a level of fine particulate matter below the safety standard, right? So these are the ones that are supposed to breathe clean and safe air. If we found an increase in mortality risk for the people that are living in a location that have a clean air, that means that the current safety standards are not safe enough, and we need to lower the standard. So you can see this is a massive amount of data in terms of total person years, because these are repeated observation over time. We have them, we have over 573 million observation. So then we enrich the data platform not only with 1 kilometer exposure, but we also have meteorological variables, we have census variables. And so you can see also the map on the left to show the level of fine particulate matter in the year 2000, and the map on the right show the level of fine particulate matter in the level 2016, in the year 2016. And you can see that there is less red in the map on the right because we have been cleaning the air quite substantially. Now, as I said, it's one of the critical elements of assessing the health impact of fine particulate matter is to be able to disentangle the cause from confounders. So when we say there is a higher risk of mortality associated with exposure for pollution, people might say, how do you know it's air pollution and it's not something else? It's smoking, it's low socioeconomic status. So we consider a lot of potential confounders, zip code level confounders that basically try to characterize additional risk factors and additional socioeconomic variables. And so confounding is one of the largest threats of any observational study, which are everywhere in data science. And so as soon as you walk away from a randomized trial, you might have a correlation between the variable that you're trying to measure its causal effect and something else that can confound. So these maps shows that the level of fine particulate matter, ozone, and nitrogen dioxide in the United States. And then the graph on the right shows the level of correlation between air pollution and many of the socioeconomic variables. As you can see that some of them have a correlation up to 0.5, right? So basically what this is saying is that if we don't break this correlation, we might misattribute the increase in mortality risk or hospitalization risk to air pollution when instead there might be something else. And that's really where it's important, the role of causal inference. So we analyzed this data using both standard, I would say, regression approaches, which is called the Cox proportional hazard model and Poisson regression approaches, but we also use the state-of-the-art of causal inference methodology, which are based on generalized propensity score. I'm gonna give you the high level idea of causal inference, which is based on matching. And then after that, I will consider just additional, I would say, technical consideration that, it's easy to digest. So basically, let me give you the fundamental idea of matching and why it's so powerful, okay? So if you look on the circle on the right, I am identifying a city in the United States, Steubenville, Ohio. It's a highly industrial city. We have a lot of high level of fine particulate matter there. There are all kinds of people living in Steubenville. There are people that are rich, people that are poor, there are people that are smokers and non-smokers, okay? So I identified one woman, her name is Jane, okay? You can see that Jane has a low socioeconomic status and lives in, Jane has a low education, it's not a smoker, and lives in Steubenville, Ohio. Okay, and now Jane, I know the unfortunate Jane died at 75-year-old. Now, what I wanted to know to do causal inference is what would have been the year of death, the age of death of Jane, if Jane itself, is called counterfactual, would have lived the entire life in Portage, where the level of pollution is much lower. Okay, so how do I figure out the counterfactual? How do I estimate what age of death would have been for Jane if Jane would have lived in Portage? Okay, well, the way to do that is called matching. And how we do that? We found the twin sister, hypothetical twin sister of Jane in Portage. We found all the women in Portage have the same age as Jane. They have the same education as Jane, eat the same diet as Jane, right? It are as similar as possible to Jane, but they have lived in Portage, and we calculate on average how long they lived. So if they lived up to 85 years old, it means that living in a less polluted city, you gain 10 years. Okay, so that is really the fundamental idea of matching, and that's what we do. Now you can see immediately realize that because we have such a powerful data set and we have pretty much everybody, we can do a very good job in matching. Now, of course, we do something more complicated because the level of the exposure is continuous, and then we need to make sure that we are approximating a randomized experiment as much as possible. So we use actually generalized propensity score matching. And you can see actually, without them going in too much into the nitty-gritty, but basically the idea is exactly the idea I gave you. It's just that we needed to match in a little bit more rigorously than has explained, but there is a paper that is available on the archive, and there is a code that you can download to basically figuring out for every gene, what are all of the twin sister genes that are breathing a different level of exposure, so we can estimate the counterfactual depth. We can figure out how much gene would have lived if Jane would have lived somewhere else and breathed cleaner hair. And that we can do that for every single individual in the entire database. Like you can see that there is when we're dealing with 60 million individuals, there is a lot of matching that we have to do. And that's why we have the code, and we are also developing a software package. Actually, there is already available a software package for you to download and use it. So what's nice about it is that when you look at this plot, by calculating and finding these matches, we create a new data set of all match observation. And the green dots show you that when you have done the matching, now we break the correlation between the potential confounders and the air pollution. And so the red dots shows the observed correlation between exposure to fine particulate matter and every single confounder when we don't do anything. And the green dots is the correlation between exposure to air pollution and every potential confounder after we have done the matching. And you can see that we have broke that this correlation doesn't exist anymore, is all below 0.1. So now we estimate the mortality risk associated with 10 units increase in fine particulate matter by using standard regression approaches and using causal inference approaches. Now, I wanted to like to point your attention to the plot on your right with the blue dots, because the plot on your right shows the causal effect of exposure to air pollution only for the population that always live in geographical areas that have fine particulate matter level below the national ambient air quality standard. So as you can see, we found strong evidence of increased mortality risk up to 13% in the regression model, and is a little lower for the other models, providing strong evidence that even if you're breathing level of fine particulate matter below the national ambient air quality standard, there is a very high risk of mortality. Now, based on this model, we found a lowering the air quality standard from 12 micrograms per cubic meter, as it is right now, to 10 micrograms per cubic meter. We will save 143,000 lives in one decade. We also estimate the exposure response curve. And so you can see that as the level of fine particulate matter increase, we have an increase in mortality rate. These are calculated as number of deaths per 100 Medicare elderly. And you can see that the shape of the exposure response function tends to be pretty linear. Now, in the last few minutes I also want to talk to you about the recent study and the study that we have conducted, that actually we have also, in addition of providing strong evidence of link between exposure to air pollution and mortality, all-cause mortality, there is also now emerging evidence and consensus in the scientific community that there is a relationship between exposure to fine particulate matter and mortality from COVID-19. We had the study, which, by the way, the entire data set and all of the code is publicly available, so you can download our data and repeat the analysis, where for the first time we show a relationship between exposure to fine particulate matter and COVID-19. We also, joined with a worldwide team, very interdisciplinary team, we estimated the number of deaths attributable. We estimated the percentage of COVID-19 deaths that are attributable to greenhouse gases emission and to fossil, particularly to fossil fuel-related emission and all anthropogenic emission. And so these numbers are pretty striking, actually. So, for example, in Europe, we have that 13% of all of the COVID-19 deaths. And by the way, this was before starting the vaccination. So 13% of COVID-19 related deaths were attributable to fossil fuel related emission and 19% to all anthropogenic emission. This number, as you can see, goes up as 15 and 27% in East Asia and 14 and 17% in North America. So with the change of administration and with the Biden administration, he recognized himself the importance of our study and many of the other studies, in really the importance these days as we're continuing to face both a climate crisis, environmental racism crisis, and a COVID-19 crisis, how important these data are to inform environmental policy. And finally, also, I want to show a dashboard that we are building, hopefully to publish soon, where actually in a single place you can review, download, and look at the worldwide evidence on the relationship between exposure to fine particulate matter and COVID-19 deaths. So you can look at all of the studies that have been published, the number of studies that provide an evidence of a relationship, harmful effect of each of the pollutants on COVID-19, the number of studies by country, and also the type of statistical approaches that different studies have provided. Again, because it's important when you are informing important regulatory policy that you're not using a single study, but you're really combining and synthesizing the whole body of evidence. So the good news is, thanks to our study and the study of many others, the WHO, the World Health Organization, has recently lowered the national mental quality standard for fine particulate matter to 12 microgram per cubic meter to 5 microgram per cubic meter. And that is wonderful news in terms of, again, breathing clean air and targeting the same sources for greenhouse gases emission. And now the Environmental Protection Agency is indeed considering as well to lower the safety standard for fine particulate matter. And you can see that here they are citing the fact that in addition, a number of recent studies have examined relationship between COVID-19 and their pollutants. So the additional scientific evidence about harmful effect of PM2.5, not only for all kinds of cardiovascular outcome and mortality, but also for COVID, has really prompted and helped in terms of moving forward with more stringent environmental regulation. Now, clearly, in 25 minutes, I just scratched the surface. So there is so many methodological challenges and data science challenges with this area of research. I'm just giving you some example. How do we quantify and propagate uncertainty? So, for example, when I told you that we are estimating machine learning models to estimate the level of pollution, well, there is uncertainty with the estimation, right? So how do we propagate uncertainty? I talked to you a little bit about causality, how we assess causality, and we can look at whether or not we are eliminating confounding from confounders that they're measured, but there are going to be challenges with unmeasured confounding, with variables that could confound the relationship between air pollution and mortality, but they haven't measured. And then there is also really the important point of open science and reproducibility of pretty much everything that we do. So I am extremely fortunate and privileged to work with an amazing group of data scientists. They're using causal inference and machine learning to assess the effectiveness of environmental policy, to look at the effect of PM2.5 and climate change related exposure on high dimensional outcome, to think about matching in the context of a generalized propensity score, and also to really identify subpopulations that are most vulnerable to this environmental exposure. And finally, the importance of assessing and be able to have a reproducible workflow, right? When I started talking to you about this gigantic data platform, there are so many decisions that we make, and it's important that the entire data pipeline is fully reproducible and open. So I just want to conclude by saying that what I've been describing is by no means only my work. We have a consortium of several investigators from many additional universities, several postdoctoral fellow, PhD student, and master student. I just want to give you just some highlight of the diversity of the team in terms of gender, race, geography, religion, and so on. And I'm really absolutely blessed to work and to learn from these junior investigator every single day. So conclusion, I think the thing to keep in mind is that the steps needed to mitigate climate change in the future are substantially the same as those needed to reduce the burden of death and disability due to air pollution in present. So to cut back on burning fossil fuel and biomass. In the meantime, machine learning and data science allow us to measure exposure and pinpoint susceptibility and vulnerability. And methods for causal inference are really powerful to better disentangle causes from confounder, especially also in the context of natural disaster. I wanted to mention that this year Nobel Prize in Economics was won by one of the winner was Guido Imbens, who was the one that really started and the founder of the field of causal inference. So in the data science, there is really an enormous amount of opportunity in data science in terms of developing new data platform that link environmental exposure to health outcome and confounders. So they have a new methodology in the data engineering to link spatial temporal data on climate and air pollution, and also to understand the distribution of effect in disadvantaged portion of the population. And I just want to conclude by putting a plug that we're also always looking for data engineering and data engineering expertise in my team. They're really interested and passionate and have the expertise to really help with building this data platform, because as you can see, that is really paramount to everything that we do. So thank you very much for your attention. I apologize for the audio glitch. This is now the new world that we live in, and I'm happy to take any questions.
Thank you very much, Francesca, for an amazing talk. Thank you very much again. Questions from the audience? Perhaps I can start with the first one. So when you do this comparison between, people who are exposed to higher pollution versus people who are exposed to lesser pollution, do you also find some probably genetic markers, or do you look for genetic markers of such exposure?
Yeah, it's an excellent question. So personally, I don't, because in our data, the wonderful thing about our data is that we have 68 million. But of course, we don't have a genetic marker and genetic information in our data for be able to assess that. But I have to say that there are a lot of additional scientists that have been looking at the effect of air pollution on DNA methylation and whether or not that is on the causal pathway for adverse health effect. And so there is an entire body of work that have been indeed found relationship between exposure to air pollution and how affect DNA and the genome, and how these changes in the genome has further exacerbated the health burden.
Thank you. Questions? We have one there. Good.
So I think it's a very challenging project. I was wondering on the granularity of the data. You said you had 60 million people. How many data points do you have per person? So you said that you found the twin sister of Jane, you have nutrition values. What do you actually know about what they eat? How many data points do you have? Do you have their location information? And can you really share it? I mean, this is quite a bit of... So how many data points do you have? And
yes, so let's start one piece at a time. So first of all, in terms of the number of observations, one in the most recent study was 550 million observations. We know the place of residence or where they live up to a zip code. Then we can, so let's say, for example, that, so we have data now from the year 2000 to 2018. And during this period, so if someone turns 65 years old on, let's say, in 2001, that person entered in our cohort, and then we can follow that person longitudinally up to 2018, or of course, before, if that person died, right? So these are longitudinal data, and I call this an open cohort because, more people are allowed to enter in the cohort every year as they are turning 65. There are two different types of data sources. The mortality data from COVID, they are aggregated, and so they are publicly available. In one of the Science Advanced paper, you can download, and I can share the data. The individual level data from Medicare, it's not publicly available, although it depends on what we mean by publicly available, in terms of that you or anyone else can get the same data that I have. It's just that you have to order and buy it and have a data user agreement with Medicare claims. So we cannot make the data publicly available ourselves. However, if you want to access the same data that we have, you have. The other information that we have on this Medicare patient, as I mentioned, so we have the place of residence based on their postal code. We have the age, gender, and race. We have whether or not are eligible to Medicaid. In the United States, if you're eligible on Medicaid, it's a pretty good surrogate of a lower socioeconomic status. And then we augment the data set with a lot of covariates that are coming from the US Census that gave you location-specific information regarding their neighbors, their socioeconomic status, the average income, weather, all of that information, and you can see all of that in the Science Advanced paper.
There.
Hi, I'm Fakir Rahman, a PhD student at Montana State University. So you gave an example of Jane where you have used a matching idea to find the hypothetical sisters. And based on that, you came up with some conclusion. So my question is that you have the data after 65 years, but let's suppose that the Jane spent her first 65 years in a highly polluted place. That could be the factor. That could be treated as a confounding factor. So did you incorporate that as well in your analysis and results? Yeah, thank you.
Yeah, it's an excellent question. Thank you. That's a very important question and a limitation. So let me see if I understand your question, because I think you point your finger on something really important. So yes, so you're absolutely right. I don't know anything about Jane, where Jane lived when she was 20. Okay, so I only know where Jane lives when she was 65. So it is entirely possible that I am, so okay, let me start back. When we look at the causal effect of PM2.5 on health, we look at the average exposure in the previous year. So we don't look at the average exposure in the lifetime. So we don't know, because the people enter in the cohort of 65 years, we cannot ascertain how much pollution Jane, was breathing in her lifetime. So we can only assess the level of pollution that Jane lived in the previous year. And so the entire analysis, when I said long-term exposure to PM2.5, I mean in the previous year. And so in the example, I don't know if I used the term lifetime, but that wasn't correct. Now, we can track whether or not the people in Medicare move. So after they turn 65, let's say that Jane is living in Steubenville for the first 3 years. And then at 82, she said, Steubenville, Ohio is too cold and I'm moving to Florida, okay? So we know that because with Medicare claims, as soon as they move, so if it's a 1 week of travel, not, but if they move, they change residence, in order to get their health insurance, they're gonna submit a claim of change residence. And so we can track that. So to summarize, a limitation of the work is definitely we can assess a lifetime exposure. We only assess the causal effect of the previous year exposure. We can go track, after they enter in the cohort, we can track where they move, and so we can take into account whether or not they move throughout post-65 and moving from the more cleaner area to more polluted area, or vice versa. But thank you, that was a really important question that I should have brought up.
Thank you very much, Francesca. That was the last question. We are already with time. Thank you very much again, Francesca, for your interesting and amazing talk and bringing another perspective into how data science can be applied to actually solve human health problems related to air pollution. Thank you very much.
Thank you. Thank you for your attention.